Well, hello and welcome YouTube. This is Mr. Robinson here with yet another math video. This time it's going to be on factoring. And factoring what? Well, factoring quadratic trinomials. That's right, kids. We're going to be looking at an a value that's not 1 in this case. And we're going to be looking at factoring these things. This is for beginners and experts alike. So if you have absolutely no idea what you're doing here, I sure hope this video serves you well, at least the very, very beginning half of it. And for experts, man, stick around. There's going to be stuff on mental factoring and a lot of examples. I want you to see this. You might really enjoy it. It's going to help you be quick and efficient in this method. So before we begin, let's talk about two principal rules of factoring. This is for everybody involved. Anytime that you factor, no matter how old or young you are, how experienced or whatever else. Rule number 1, this is a golden rule. When factoring, always find your common factors first. Make sure you factor those things out. And I'm talking about greatest common factors. Let's take a look at these 3 examples. I'll show you what I mean. We have a 2x squared plus 12x plus 10. You could factor out this quadratic if you know how to factor out non-1 quadratic coefficients. It's possible. But when you do so, your answer will still have a common factor of something, so you wouldn't have factored it out completely. So just begin by doing that anyway, because if you have to do it at one point, you might as well start at the beginning for 2 reasons. Number 1, so you don't forget later. And number 2, factoring this quadratic that I just wrote inside here, x squared plus 6x plus 5, is so much easier than factoring this 2x squared plus 12x plus 10. This one takes a little bit longer, and I'll be sure to talk about how you factor out quadratics where your quadratic coefficient isn't 1. But when it is 1, it's a lot easier. And I'm not really going to explain how to do it right now. I'll just write out what this answer becomes here. So when I box this thing out, you'll see that I took the 2 and factored it out. All of these numbers divided by 2. And then I left this 2 outside of here. You see, I can't ignore it. It doesn't go away. But I did factor this inside quadratic right here, and it became x plus 5 times x plus 1. And that's your final answer. If I distributed this all back out, it would become this original polynomial. So same with these next 2 problems. X cubed minus 16x squared plus 63x. And you might be sitting here going, well, even if I know how to factor quadratics, I don't know how to factor cubics. Well, that's okay, because take a look. Every term has a factor of x. So I'm going to factor that x out, and what's left is x squared minus 16x plus 63. And now I leave this x on the outside and I factor the inside. I'm going to factor this out to x minus 9 times x minus 7 on the inside, and that would be my final answer. And again, if you don't know how to factor these out yet, that's okay. You can go back to these and take a look and practice them at the end. I'm just talking about why I'm doing the common factors first. It really helps when all is said and done. And the last one right here, 9x squared plus 12x minus 45, again, look for that common factor. 9 and negative 45 can both divide by 9. Unfortunately, 12 cannot. However, these can all divide by 3. And I factor this 3 out, and I'm left with 3x squared plus 12x, plus 4x minus 15, I think. And so the 3 stays on the outside, and if this is factorable afterward, I'm going to go ahead and whittle it down to what it is. If it's not, I would leave my answer like this. And, you know, you're looking at this and going, well, Mr. Robinson, this 3 still remains. I don't have a quadratic coefficient of 1. You said that let's make it easier when it's a 1, and this one's not. Well, guess what? It's also easier when the numbers are smaller. It's a lot easier when the numbers are smaller. You'll probably see why in the end. So let me try and factor this here. Just give me a moment. This is my mental factoring taking place right now. We got the so we got a plus 5. No, plus 3 minus 5. Okay. All right, so this will be our answer here. 3x minus 5 and x plus 3. So again, there's a mental process I just did. You even saw me make a mistake. It happens. But this was factorable. Factored out to this right here, and I'm good. Now again, if you don't know how to do it yet, that's okay. It's okay. I haven't started yet. I'm talking about finding common factors first, and you can kind of clearly start to see a reason why, especially with the first 2. I promise you, this problem was a lot easier when I took this 3 out, as opposed to what I would do here. And again, you would have to factor that out anyway in the end. You would have to factor that 2 out or that 3 out in the end anyway, because one of these quantities would have still had a common factor of 3. One of these quantities would have still had a common factor of 2. The x, man, that's a lot harder to look at and say what you would do with these things here if if you didn't factor that out. You would really have to factor that one out first, because you really got to look at this as a quadratic trinomial. Okay, the second principal rule is if the leading coefficient is negative, factor out that negative. And trust me, you will thank me later on this, I promise. You know, when it comes to this factoring stuff, you're really used to just seeing x and x, maybe something else right here, but they're positive. And they're positive, and because when you do what's called foiling or distributing, you are going to be multiplying that x by other numbers. And you don't want that one of those x's to be negative and mess up everything else you're trying to do. Because I can't just look at this problem and say, what do numbers multiply to 42 and add to -1, which is, of course, the kind of question you'd ask in these problems. I can't ask that here because this x is negative. The x squared, is negative. And that would mean when I factor this thing out here, I'd be looking at one of these being negative and one being positive. And you don't want to multiply a negative with another number. It doesn't work right. It doesn't work right. So begin by factoring out that negative. And a negative, technically I'm factoring out a -1. But they generally don't write that. And what you're going to do is basically write all the signs in reverse of what they were before. So this negative becomes a positive, this negative becomes a positive, this positive becomes a negative. As you distribute back in, you can see how this would become that. So just like these numbers stay on the outside, or this variable, this negative will stay on the outside as well. And I'm going to factor out the inside. And of course, again, I'm not quite explaining how this is done just yet. If you're an expert, you probably know exactly what I just did. But I started off by factoring out that negative. Makes it so much easier. It really does. Begin with that. This negative right here, this is the negative for the quadratic coefficient, so let's factor it out. But also look at this rule. Always find common factors. All of these numbers can divide by 4. So I'm going to do that to begin with, but I'm also going to make sure to divide out the negative. So when the -4 factors out here, left in this term is just an x squared. Left in this term, 32 divided by -4 is -8. And there's the x right there. -48 divided by -4 is a positive 12. And in factoring this, assuming it's factorable, it looks like it is here. We'll get x minus 6 and x minus 2. And it's going to factor to that. And again, this is helping me, in the end, factor. You will thank me for these things that are going on here. The last example, 9 minus x squared plus 8. And you might say, hey, the leading coefficient isn't negative. But I'm going to say, hey, this isn't the leading coefficient. The quadratic is the leading coefficient. This is a quadratic polynomial. The largest degree is 2. So what I'm going to do is rewrite this with the quadratic term first, the linear term next, and then the constant term last. So there you go, these 3 terms. Now I'm going to factor out the negative and then go to town just like I did the last 2 problems there. So in solving these problems here, let me figure out what this is first. Minus 9 plus 1. So in solving these problems here, it was achieved much more easily by doing things. Now, there are a lot of problems where there are no common factors and there are no leading negatives. So you still looked for them, and then you said, okay, they weren't there, and then you move on. So, folks, let's move on. All right, I'm going to lay out the 3 preferential styles of factoring that I'm going to be playing with here today. The first one is the most, it's the most standard practice, as this says right here. It's called factoring by grouping. It is a standard practice often used when you're factoring cubic polynomials. I'm talking about those ones that are like larger, like an x cubed minus 6x squared, plus 5x minus 30, something like that. You can factor this by grouping if you pair off some things right here, if it's factorable. I think that one is when I set it up. And you can get this into 2 binomial quantities. Of course, I'm going to go over that practice later, but it's the standard practice for that. So, case in point, you got to know how to do this. This is designed to plainly understand common factors. So when you're really looking for the GCF of some values here, it's used quite a bit. And really understanding how quantities factor out of each other. That's the first one I'm going to talk about today. Then we'll talk about the generic rectangle. And this is one, I call it a foolproof system. If you know how generic rectangles lay out, you're not really going to make a mistake when you're doing this method here. It's a nice visual layout. It expresses the standard form of the polynomial as the rectangle's area. So you're going to have a rectangle right here. It's going to be divided into portions, like boom, boom. And this is going to be the area of it when you're writing out the polynomial. The factored form will be the dimensions, like the base times height, these things right here. So this times this equals that. Or this can factor out into this and that. It's a really nice layout, and a lot of students really like it, but it's a process that you want to break at some point because factoring is a lot more than just a rectangle. It's a nice visual aid, but over time, you want to really look at some other ones, and here's the one I want to point to. Mental math, or educated trial and error, as I call it. It's kind of trial and error, but there's a lot of, I'm not going to say smarts that go into it, but there's a lot of selective filtering. You know what you're going to try and what you're not going to. And there's a lot of mental stuff involved. You can write things out, but it's designed for those who really know their times tables, are good at mental storage of numbers, tried and computed, and understand the gist behind polynomial distribution. You really got to know how the FOIL method works. It is very efficient and streamlined when done right. This is the one that I hope that most people try and go to, especially if you're considered an expert in this. And that's the last one I'll be talking about. And I'm going to do plenty of examples. I'm going to do at least 10 examples of these, 4 of these, and 4 of these. I'll start with these 4, then these 4, then these 10. Of course, I'm going to talk about these as well. Okay, so to really get into factoring, instead of talking about ax squared plus bx plus c, first let's talk about the basic question involved when factoring x squared plus bx plus c, when your a value is 1 here. The question was, when factoring this way, what two numbers multiply to become c and add to become b? So what two numbers multiply to become your constant term and add to become your linear coefficient? And this is also what the diamond method is used for. If you use that visual aid, that's the question that you're asking yourself. When you use this, which I'm not going to use it, you say what two numbers multiply to this and add to this, and then those become your two numbers you write right there. If you've seen that before, you know what I'm talking about. That's what I'm using here, only I'm not going to draw out a diamond when I do it. This is because in FOIL, those two linear terms, the O and I, outside and inside in FOIL, they multiply only by an x term. So like I'm going to take a look at this example and show you a lot of different ways here. I'll go ahead and start off with FOIL to explain it. When you FOIL x minus 7 times x plus 5 here, first you do x times x, which is x squared, but then the outside, the O, is x times 5. Notice what the coefficient is. It's just 5x. The coefficient of the linear term is the same as that value here, as the constant in the quantity. Then I have x times negative 7, which is negative 7x. Notice how that negative 7 appears down here. So these two values will add together because they're both the linear terms. They'll combine. And I have negative 7 times 5, which is negative 35. So take a look. This is a 5 and a negative 7. This number is 5 times negative 7. This 5 and negative 7 will combine through addition. 5 plus negative 7 is 5 minus 7. And you get x squared minus 2x. So 5 minus 7. And this is 5 times negative 7 minus 35. That would be your final answer there. Okay. So that's the great question that you got to ask. You just got to say, well, what two numbers add to become this and multiply to become this? And there's some nice ways of going about it. I've talked about them before, so I'm not really going to dive into that too much. You will see me do selective filtering with this, though. I'm going to pick factors of the number 35, and then I will, by a very educated manner, determine which values I should try to be positive and negative to begin with anyway. I may explain that down the line. So the two numbers that represent the product are also the two numbers that represent the sum. The two numbers that multiply to C are also the same two numbers that add to become B. And that's a great and easy way of going about this. So that way, when you find those numbers, you can just write your factoring out in this form. Now I'm going to show two different visuals of this because foiling, the FOIL method is going to be most important for when we talk about the mental factoring. This quantitative distribution method is most important when we talk about factoring by grouping. And then the generic rectangle, of course, is very important for when we talk about factoring using the generic rectangle. So I might point back to this slide at the very end, or not the very end, but when I start introducing these concepts to say, okay, this is us going backwards into here. Because when I went from FOIL, or from here down to here, I did what's called distribution. I distributed this factored quantity into standard form. What we're going to do is we're going to be factoring this standard form into factored form. That's how we're going to be writing this. So we want to be able to go backwards from here up to here. That's the whole point. So quantitative distribution, I'll take that x minus 7 times x plus 5, and instead of doing FOIL, what I first taught with my students was I said, let's take the entire quantity right here, x minus 7, and let's multiply it by each term in the polynomial. After all, in the quantity. After all, that's what you would do by normal distribution, right? This a would multiply by b and c. So this x minus 7, the number on the outside, will multiply by the x and the 5. So in doing so, what you're going to do is x minus 7 times x is the same as writing x times x minus 7, just commutative property of multiplication. This looks a little better than writing the x on the end. And x minus 7 times 5 is the same as 5 times x minus 7. So what I've achieved in this case right here is I'm now able to distribute this x into the x in the negative 7 and this 5 into the x in the negative 7. And then I'll get x squared minus 7x plus 5x minus 35, which looks just like this one, only the 5x and negative 7x are switched. That's okay. Addition's also commutative. And you'd get this answer down as a result again. Now this portion right here, I want you to take note right now, because otherwise it'll be confusing when I talk about factoring by grouping. These two right here had a common factor of x. These two right here had a common factor of 5. This x minus 7 was identical in both of these guys right here, and I factor out the x minus 7 to leave me with x plus 5. Just like I've distributed this x minus 7 into this x and this 5. That is the idea of factoring by grouping when we go that way. You will be sure to see that again. I just wanted to point to it now. And the last one, generic rectangle right here, what I'm going to do is just draw out one of those rectangles, divide it into 4 portions. And on the outside, I'm going to take my items here, this x and this negative 7. They will share separate parts of one side. And this x and this 5 will share separate parts of this one side. And to multiply these two is to essentially find the area of this rectangle here. Now what's great about rectangles, as poorly drawn as this is, but what's great about rectangles is that opposite sides are equal. So if this is x minus 7, then this is x minus 7. And by the way, so is this. So if this is x, then this is x, and this is also x. I'm just going to write the x right here, but what's great is if I want to find the area of individual parts, like this x times x to get x squared, I can take this x, and I can also say, to find the area of this rectangle, I'm going to do 5 times x, because if this is x, then this is x. So x times 5 right there, boom, becomes 5x. That's what I'm going to multiply. That's the area of this little portion of this bigger rectangle. And x over here times negative 7 is negative 7x. And then 5 times negative 7 is negative 35. And what I'm going to do is write this out as a string right here, x squared plus 5x minus 7x minus 35. If I want to find the area of this rectangle, I am going to add up all of these individual portions. I will not multiply them. They already multiplied to become the area of the small parts. Now that I add all these areas together, it becomes that, which of course turns back into this again, just like all these other ones did. This will be important when we talk about factoring generic rectangles. You'll start with something inside here, and you'll find out what the things could become on the outside. So you've seen all 3 different ways that we distributed. Now we're going to factor going the opposite ways here. But before doing that, we need to talk about what it means to have an a value that is not 1. So when factoring ax squared plus bx plus c, assuming a doesn't equal 1 and all common factors are factored out, the question now becomes, what do numbers multiply to become a times c? Not just c this time, but a times c, and add to become b. Now why is this important? Why is it important to say a times c now? Well, I'll let you know. I just want to let you know right now that this is us assuming a does not equal 1. However, when a does equal 1, what is 1 times c? Well, that answer is c. 1 times c is c. So when you look back at this, that question is the same question. Multiplies to become c because that a is a 1. So we are doing a times c even here. However, you don't want to be distracted with that. You don't want to be distracted just asking yourself what's 1 times c each time. Just look at that number. You won't have to know. So here, though, this a value does matter now. And I'm talking about if there's no common factor or that we factored those out and there's still a non-1 a value. This is because when you FOIL, and this time I'm only really going to do FOIL, not generic rectangles, this and that. One or both of the linear terms is multiplied by an x term that contains a non-1 coefficient. That sounds really confusing. Let's see what that looks like before I keep going with that sentence. When I FOIL this, I'm going to do 2x times x. That gives me 2x squared. When I do 2x times 5, that gives me 10x. Negative 7 times x is negative 7x. Negative 7 times 5 is negative 35. Now, this 10x is different from what we saw from the other problem. And by the way, I want you to take a close look at this problem. If I hid this 2x, what does that say? X minus 7 times x plus 5. Look at the previous problem we did, x minus 7 times x plus 5. I'm going to show you that this problem becomes a significantly different answer. Well, there are some parts that are the same, but it becomes a different answer than what we had before, because take a look at this 10x. Remember before when we multiplied something with that 5, it became a 5x and a 5x and a 5x? Well, not anymore. Now it's a 10x. Why? Because one of the linear terms, this 10x, was multiplied. To get this number, this is a number that was doubled. A number was doubled. 5 was multiplied by 2x, an x term that contains a non-1 coefficient. This 2x is a non-1 coefficient of 2. 2x times 5 is 10x. Now, this is important because your two numbers, negative 7 and 5, aren't the two numbers that become your x's, so these two don't add to become your b value. These two add to become your b value. 10 minus 7 is 3, and this is your final answer. So you can't ask anymore what two numbers multiply to c and add to b, because there are no two numbers that multiply to this and add to this. Negative 35, if I tried that 7 minus 5, even, that would be 2x. It's very close, but it's still not very close. That's not the answer. That's not how we approach it. What you actually have to do is take a look at the fact that negative 7 times 5 may be negative 35, but the negative 7 and 5 aren't these ones here. And I know I'm kind of saying the same thing over and over. I have to stress it. That's why. So the constants in the quantities are not necessarily the coefficients of the linear terms. Now, sometimes they are. For example, x times negative 7 was negative 7x. So this negative 7 was this negative 7. But this 5 right here turns into a 10 because it was doubled. So what's important to note is that, yes, this was 2 times 5. So the 5 still exists there. That 5 still kind of matters, but it's more important to look at 2 times 5. So what we're actually trying to find now is that the numbers that represent the sum, 10 and negative 7, are the two numbers that we're actually trying to look for. So when you're asking what two numbers, blah, 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 and blah, 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 the answer to our question will be 10 and negative 7. Now, those two numbers add to 3. So what are we going to look for what they multiply to? Well, 10 times negative 7 is negative 70. What's great is even though you don't know these numbers yet, when you start off here, you have two other numbers that can help give it to you, and this will always be true. 2 times negative 35 is also negative 70. So the good news is you'll have your a value and your c value always multiply to become the same thing as what the sum of this value is. So you're going to look for the two numbers that multiply to become negative 70 based on these two, and then the ones that add to 3 based on that. That's how we're going to be doing these problems. So we must still find the numbers that become the sum, and the product of a and c will always match the two numbers that represent the sum. That's great. That's great. If you actually saw here in this generic rectangle, this actually will show up here as well. This 1 and this negative 35 together will multiply to become the same thing as this negative 7 and this 5. Those both multiply to become negative 35. That's very cool to see as well. It does always happen. I'll be sure to show you that. And here's another example here just to show, what if I keep that same x minus 7x plus 5, but this time I have an 8 in front? How's that going to change things? Well, in foiling, 8x times x is 8x squared. 8x times 5 outside is 40x. Whew, now the number changed. Negative 7 times x is still a negative 7x, and negative 7 times 5 is negative 35. You can see how this becomes your answer. So clearly, the linear term is affected somehow by that 2 and by that 8. When you factor, and you can't factor an 8 out of here because it's not a common factor of anything involved here, but when you factor and this 8 is involved, you need to recognize that this is really changing something. It's really changing that 5. Now, the negative 35 remained because your last terms, negative 7 and 5, well, are still negative 7 and 5. So nothing there actually changed. But this 5 was now, I don't know what the word is, octupled? It was multiplied by 8. So it really changes things. Now, there could have been another number here like a 3, and I could have multiplied negative 7 by 3, and that would have changed as well. So the constants and the quantities are not necessarily the same as the coefficients of the linear terms. One or both of them will be affected. In this case, I only affected the 5, not the negative 7. So in terms of factoring, because I'm going to go ahead and start in a moment, keep this in mind. I'm going to ask this question: what two numbers multiply to become a times c and add to become b? Okay, let's begin with factoring by grouping. First thing you're going to do is find your two factors, meaning find the answer to this question. Find the answer to this question. And then you will write out your expression. You will rewrite it so that the linear terms are now separated, and the order in which you write these two terms ultimately will not matter. Okay, let's put a break right there. Let's see if we can start with that. I have a problem down here, factor 7x squared minus 32x minus 60. And I want to go ahead and, I want to solve this thing. And I'm going to do this without a calculator. It might take a moment, so, give me that. I'm not going to ask what two numbers multiply to negative 60 and add to negative 32. I'm actually going to multiply the 7 by this negative 60. And by the way, I already mentally did my first principal golden rule. Is there a common factor among these three terms here? No. 7's a prime number. That means the only number I could divide out is a 7. Negative 32 and negative 60 do not divide by 7. So I'm stuck with what I have. So I have to take the 7 and multiply by negative 60 to get my a times c value. 7 times negative 60 is negative 420. This negative 420 is the same thing that the two numbers that add to negative 32 multiply to become. So I'm asking the question, what two numbers multiply to become negative 420 and add to become negative 32? Now, in doing so, here's going to be my selective filtering process. I'm going to list as many factors of 420 as I can and as I know. And I'm going to try and do this without a calculator. I'll let you know I haven't done this problem yet. So I'm going to start with 1 and 420, of course. And I'm just going to keep dividing as long as I can here. 2 and 210. 42 divided by 3 is 14, so this is 3 and 140. 4 and 105. 5 and 84. 6, 6 and 60, 70. I don't know why that took me so long. That was bad. 7 and 60, right? That should work out. Wow, all these things divide. That's great. I mean, not so much because I'd have to test a lot. 8, I don't think this divides by 8. 450. No, it doesn't divide by 8. 9, you have to give me a moment on some of these. I apologize. However, it doesn't divide by 9. 10 and 42. 11, I somehow doubt 11. I'm just going to skip it for now, and if I have to, I'll go back. 12. 120. 12. 12 and 35. 13, 14. If 140 was here, then 14 and 30. Now, how long should I go? I'm going to keep going until I reach these two numbers as being the same, or until one number goes larger than the other, if that makes sense. 15. I somehow feel like 15 works because 30 worked. So 15 must be 28, right? If I divide this by 2 to get this, I multiply this by 2 to get that. See, that's the kind of, if you can get really good at that kind of stuff, that would be excellent. I got to think if 16 works. I don't think so, because 16 goes, no, wait. It does not. 17, I want to say 17 doesn't work. I'll just say it doesn't. 18, did 180 work? No. Will 18 work? 18 is 80 in it, multiple of 80. No, I don't think that works. 19, no. 20 should. 20 gives you 21, I think. And that's where I should stop because, right, when I divide by 21, I'll get 20 back. So then I'd just be repeating these numbers again. Okay, that was the longest, to be honest, that was one of the longest lists of factoring I'd ever done. Now, this is a part of the mental factoring approach. When it comes to this stuff here, when you ask what two numbers multiply this and out of this, I came with a big list of numbers there. Okay, here's my selective filtering process. My product is negative, and my sum is negative. Excuse me, my product here is negative, and my sum is negative. That means I'll have a negative times a positive, and the negative number will be larger. Otherwise, I'd get a positive sum. So I'm going to test all of these. Notice how I listed the smaller numbers first and the larger numbers second here. That allows me to do this. So I'm going to get negative 419. Of course not. Negative 208. And you know what? You're trying to look for negative 32. Is 3 minus 140 going to be negative 32? I don't think so. I think you can take some out and then kind of press your luck later. 6 minus 70? No, come on. No, come on. 7 minus 60 is still negative 53. Here it is. This one's negative 32. I'm glad this was factorable. If it wasn't, this would have been a waste of our time, right? 10 minus 42 is negative 32. I've found my two numbers. 10 times negative 42 is negative 420. And 10 minus 42 is negative 32. Now, if I'm going to be honest here, in my head, I would have gone for the more obvious numbers of 420 first just in case they worked. This probably would have been the first number I would have tested. I mean, I'm being honest. 10 times 42 gives 420, right? That stands out pretty well. So that's the first thing I have to do there, find my two factors. Boom, I found them. And I know that took a while. And by the way, I'm going to do this example 3 times. And in doing so, we already know our factors for it. Okay, write out your expression so that the linear terms are now separated. So this 7x squared minus 32x minus 60 will turn into 7x squared plus 10x minus 42x minus 60. So I turned this into this. The negative 32x is now a 10x minus 42x. Well, that's good and great. So what does this allow me to do? First of all, the order in which I write these doesn't matter. Personally, I would have preferred to write the negative 42 here because I know I can divide that by 7. But that's neither here nor there. I'm here to show you it doesn't matter. Excuse me. Your trinomial is now 4 terms instead of 3. Pair off neighboring terms, the quadratic with the linear right next to it, and the linear with the constant right next to it, and find their greatest common factors. I should say greatest common factors, the GCF. So I'm going to pair off the quadratic term with the linear term that are right next to each other. I'm going to find a common factor among those two terms. And the linear and the constant terms that are right next to each other, I'm also going to find a common factor for those as well. The ultimate goal for this is for the factored out quantities to appear identical to one another at all costs. That way the two items will have common factors themselves. Now, what does that mean? What I'm going to do, first of all, before I factor this stuff, I'm going to go back to what we had right over here, way over here. And you see how these things are paired off right here. There's a common factor of x, and that gives me x times x minus 7. There's a common factor here of 5, and here I get 5 times x minus 7. These x minus 7s are the same. This is a very important step. If these aren't the same, you can't do the next step of factoring out that x minus 7. Because if it's not the same, then you can't factor it out. So in doing this over here, I'm going to make sure I just find the largest common factor of this part right here. It's going to work out very well for me to do so. And as I write out that result, there's a common factor of x here. So I'm going to be left with 7x plus 10 inside of here. It doesn't look that great to you. That's why I really like factoring the other way. I will show you factoring by reversing these, why sometimes it's better, even though it doesn't matter. And these two right here, what's the greatest common factor of 42 and 60? I'm thinking the number is 6. I think the number is 6. Now here's the thing. If I factor out just a 6, what am I left with? I'm left with a negative 7x minus 10. This is no good. This is no good because 7x plus 10 and negative 7x minus 10 aren't the same thing. They look pretty close. In fact, if only I factored out that negative from both of these things. Gosh darn it, those negatives. So what I'm going to do instead of factoring out a 6, I'm going to factor out a negative 6. Because I want this thing inside here to say 7x plus 10. So essentially, you're kind of doing this. You're kind of asking yourself, what's the greatest common factor here? And what's left? Okay, I want this to be left here. What do I have to factor out? That's kind of what's being asked. And this was the greatest common factor here and here. Now, I'm going to factor these quantities out. I'm going to factor out this 7x plus 10 from both terms. Remember how back on this slide, the x minus 7 factored out of both of these items right here. And what was left when I factored the x minus 7 out of here? Just an x. And what was left when I factored this x minus 7 out of here? Just a 5. So x plus 5 will be all that's left in the other quantity. So let's go ahead and do that here. Finish this one off. 7x minus 10 is going to factor, 7x minus 10 is going to factor out of both terms here. Okay, so I'm going to factor out the 7x minus 10, plus 10. And when I factor the 7x plus 10 out of that quantity right there, all that's left is x. And when I factor the 7x plus 10 out of that one, all that's left is a negative 6. I'll have x minus 6. That is our final answer to this problem. I have factored this one out by grouping. I did the grouping step right here. I neighbored these ones off, and it all panned out, right? It all worked out. Now, I just did that writing the 10x minus 42. What if instead I wrote this as minus 42x plus 10x? Whoops, that's a 4x. What if I wrote minus 42x plus 10x instead? And then minus 60. Now, you can see, first of all, the order will not matter when we do this. Where did I write that? The order in which you write these two terms ultimately will not matter. So whether I write the 10x first and the negative 42x second, or the negative 42x first and the 10x second, it won't matter. I kind of like how I write it this way, though, because I can more clearly see my common factors. I know that 7 and 42 has a 7. You know, the more you do this, the more you'll kind of realize what's going on there. So I can factor 7 and an x out, and I'll be left with x minus 6. And here, I can clearly factor a 10 out, and I'll be left with x minus 6. So you can now see these match up the x minus 6's, and when I factor out the x minus 6's, I'm left with a 7x plus a 10 together. And you can see how these ones match. I tend to write the larger number first with these. That's why I wrote this one last and whatever else. Plus they match. But that'll be your final answer, 7x plus 10 times x minus 6. And there we go. We're set to jet. That's it. So that's how you factor by grouping. You first find these factors and you write out the string. Then you pair these off and find the greatest common factor among them. Then factor those quantities out to have your final result. I'll be sure to do 4 more of those problems of much smaller values later. Okay, generic rectangle factoring. We're going to find our two factors again. Now, we have the exact same problem, so we already know that our numbers that we're going to be looking at are a 10 and a negative 42. I'm not going to go through that process again. You go through that process in finding your two factors. Then create a rectangle divided into 4 parts like so. Yeah, you see that? We're going to write the quadratic and constant terms diagonally opposite each other, and our two factors will be written as linear terms diagonally opposite each other. This will not work if you do not do this. If you do not write this in that exact way, diagonally opposite each other, this will not work. So we have the 7x squared. I'm going to go ahead and write it in this corner. Now, it doesn't matter what corner you start it in. It just matters how the other terms relate to it. There's the 7x squared. The constant term is going to be a negative 60. I'm going to write it diagonally opposite the quadratic term right here. This 10 and this negative 42 will be written as a 10x and a negative 42x diagonally opposite each other as well. Now you might remember that on this slide here, I circled these and I said, hey, these will always multiply to be the same thing as what these multiply to become. Now remember, I didn't get these terms except from here. So when I distributed these, I got these written out this way. It naturally appeared that the quadratic term, this x times x, was diagonally opposite the constant term, negative 7 times 5. So we have to make sure we set up that same rule. Now, in confirming that we set it up well enough, let's go ahead and take a look at the fact that the 7 times negative 60, which is negative 420, is the same thing as 10 times negative 42, which is negative 420. Those should both give you negative 420 when multiplied. That means I'm set up for success right here. Okay, The original polynomial represents the rectangle's entire area. So here, when I add these up together, that represents the area of said rectangle. What I'm going to do is I'm going to write some values outside here, the dimensions of this rectangle, if you will. And they're divided into parts. So this portion of this rectangle is split up into a base times a height. This portion is split up into a base times a height, and etc. Base times height, base times height. And as we said, a rectangle's sides are equal, so this side length is equal to this side length. Excuse me, opposite side lengths are equal. So whatever I write here should be able to apply to this rectangle down below. So what I'm going to do is factor out these individual parts, and I will have to look at them close enough and make sure they relate in a way that helps me. For example, I know that I shouldn't be writing something like, if I'm going to get 7x squared, I can't do something like 7 times x squared. For several reasons. First of all, this x squared has to relate to this rectangle right here, and x squared times no good polynomial term will help me give me a negative 42x. This squared is bothering me here. Also, this 7 right here, don't multiply with that 10 down there. I'll deal with the 7 last. I'm going to deal with the x's first. If I have an x squared and these two terms have x's, then these two portions of these sides need to have x's. I need this to have an x to help me with this value here. I need to have an x that will help me with this value here. Okay? And those x's can't leak into this negative 60 at all. So as you can see, these values won't have x. These parts should never combine with their neighboring parts. I shouldn't have an x right here, otherwise these would combine. So what am I going to do next? What I'm going to do is take a look at this 7 right here. And I'm going to say, okay, how do I get 7? By 7 times 1. Okay, so I can either make this a 7 and this a 1, which is no good for me because even though 1 times negative 42 gives me negative 42, there's no integer I can multiply 7 by to give me 10. So I must have written these out the wrong way. What if I instead write the 7 out over here? See, this is where you might need a pencil and an eraser. The 7 times, hey, negative 6 gives me negative 42. And by the way, 7x times negative 6 gives me negative 42x. Well, that's good. I got something that'll work out there. And then this x, this 1x times 10 gives me a 10x. And just for good measure, negative 6 times 10 gives me negative 60. So this one pans out to work exactly as I want it to here as I write this out. So this visual aid is really nice. I know people really like it. And it's good help and good fun when you're working on perimeter and area of subportions of rectangles and like terms. And it's nice. It's just that there's more to be had here. There's more thought that I want you to try. Anyway, dividing the rectangle into these portions allows you to break the sides up into parts, as I did. The lengths of these parts represent the greatest common factors of the two portions to which you're referring to. These parts should never combine. And guess what I have here? If I multiply this times this, I get this inside. This represents this. And these two parts represent the lengths of the sides. If I add this side with this side, I get the entire height. If I add this side with this side, I get the entire base. And if I multiply them together, I should be getting that area. So this is the factored form, 7x plus 10 times x minus 6. Base times height equals that. So good. I'm going to make sure to do 4 more problems with that generic rectangle, but that's the understanding behind it, the setup, and what you're trying to accomplish there. Okay, here's the meat and potatoes of this video, mental factoring. And I know this will not be as easy done. This is much easier said than done. This will not be done as easily as I will say it. And actually, what I explain will kind of be tricky. That's why I'm going to make sure to do 10 problems of these and make sure I really got it. This is really backwards thinking. We have to wholly understand how FOIL works, how we distribute polynomials, what happens when you're doing that. Recognizing that the quadratic term is a product of your first two terms in the quantities, the coefficients and all. So this 7x squared is a product of something times something in these first two terms here. And you'll see this x and x right here. X times x is x squared. Something else times something else gives me 7x squared. The linear term, the ultimate linear term, this negative 32x, it's a sum of your two other terms, of the two other linear terms, which are derived from multiplying the outside and inside terms in the quantities. Here's the big part. These terms are no longer necessarily matching the last terms because now they are potentially multiplying by terms whose coefficients are not 1. What does that all mean? Let's go back to when I FOILed this back here. Remember when we multiplied x by 5, we got 5x, and negative 7 times x, we got negative 7x? Yeah, unfortunately, now that we're mentally factoring quadratic coefficients, quadratic polynomials with a non-1 coefficient, this 5 will no longer necessarily just be a 5x. And this negative 7 here will no longer necessarily just give you negative 7x, as demonstrated in these problems right here. This negative 7x may have still been here, but this 5 is no longer here. You have to understand that the outside term or the inside term or both may be multiplied by whatever your first terms are in each quantity. Notice this isn't just x times x anymore. This is 2x times x, which by the way gave me 2x squared. That makes sense. So if you're looking at this problem here, and I know I'm kind of working ahead talking about this 7x squared here, I know that it's not just going to be x times x anymore. In fact, as 7's a prime number, and like I said, I know I'm working ahead, I know this will probably be a 7x times x. That's what gives you 7x squared. So as I'm looking at these two values here, you have to understand that when I FOIL, somewhere I'm going to be doing 7x times whatever this number is. That means this number that I'm looking for will be multiplied by 7. It will be 7 times larger. And that number is a part of your sum. This is the hard part of this. Figuring out what these become, trying to pick numbers that makes your sum match up to what you want. And then your constant term, of course, is the product of the last two terms of the quantities, this negative 60. So here's how we're going to do this problem. Begin by writing out the parentheses of factored form, placing the variable in both, x times x. So let me erase the 7x for a moment. I'm just going to write this out as I did. So I'm going to start off each problem going 7x squared minus 32x minus 60. If it's factorable, it should probably turn out to look like an x times x ordeal. Maybe even there's a number in front of here I don't yet know. Now comes trial and error. Choose any factor pair of your quadratic coefficient. My quadratic coefficient is 7. The only factor pairs I can choose are 7 times 1. You can choose 1 times 7, but that's the same thing. I tend to like to write the bigger number first. That's just how I do it. Now, what's great about this part of this problem so far is that this was a prime number. That means 7x times x is a guarantee that that's what these will become. I have locked those in. If this is factorable, this is the only way this is going to be produced. I don't have to do anything else with these. And test these values against all factor pairs of your constant term. By that, I mean I'm going to mentally be foiling with pairs of values that I'm going to try plugging into here and here until my solution works. Keep trying until it works out. Now, there will be factors of my constant term. So now what I'm going to do is I'm just going to pick factors of negative 60. And I'm going to try them and FOIL out these until I get a negative 32x with my inside terms. So try this. Okay. Now I know this isn't. I know that we already know the answer to this sort of, and I'm going to try and dodge that answer a couple of times just so I can really talk about what's going on here. Factors of negative 60. How about 1 and negative 60? Okay, well, 7 times negative 60 is negative 420. I don't think that's going to add to negative 32. I'm going to erase those. But here's what you also have to try. You can't just try a 1 and a negative 60 here. You might have to try a negative 60 and a 1 right here. Now, notice how I'm testing it. I want to make sure that the product of these two is still smaller than the product of these two. I want to make sure the negative result is still bigger because this number is negative and is smaller. Now, if you don't really know which way to do it, the good news is if you make this a negative and this a positive, it'll just be the opposite of your answer. For example, 7 times 1 is 7, and negative 60 times x is negative 60. That gives you negative 53, which of course isn't the answer. But as I try this as a positive 60 and this as a negative 1, that'll give me negative 7x plus 60, which is 53x. So even if you get the opposite, even if I tested these until I got a 32, I would just know I'd just have to switch the signs, and that's all. I like to not think of it that way. I like to try and get the signs to match. That's just me. It's just how I subconsciously do these problems. Now, those aren't the numbers there, so obviously 60 and 1 are out. You might even try some other ones like 2 and 30. And 2 and 30 is actually not a bad guess. Now, here's the educated part about this. Notice how I put 60 here last time I did 7 times 60. Way too big. 7 times 30 here will also be way too big. So I know if I try a 30, I'm going to try it right here. And I'll try this one as the negative and this as the positive 2 here. That's 14 minus 30. That's negative 16. That's not going to work. So you see what I'm doing here? I'm trying numbers until this works. And really, I don't actually normally write them out. I've stored which ones I've tried, and I throw them to the wayside after that. Now, these are a lot of numbers that multiply to 60, so you might be going a while as you're practicing this. Not all problems will be this long. In fact, the 10 problems I do after this, we're probably not going to get larger factors like this. We may, time to time, but most often you won't. All right, let's go bold here. Let's try something like 12 times 5. That's 60. So let's, you have to kind of test things along the way. Let's try a negative 5. See, the only way this would work is if this was like a negative 5 and negative 12 maybe, because now 35 and 30, I don't know, but that doesn't work here. Negative 35 plus 12 is negative 23, no good. Anyway, you keep trying. Eventually, of course, you're going to land on this answer here. I believe it was a positive 10 and a negative 6. And you're going to land on this answer. This is negative 42 plus 10, which is negative 32. And it feels so good to get the right answer. And then you go and circle that in. That's it. Now, this was a hard problem to do. There are a lot of numbers you're going to test. The more you know how to multiply. See, that's why I said you have to be good at times tables. I don't know where I said it. Right here. Designed for those who really know their times tables. And you know how to store numbers in your head mentally. Because it's not just about multiplying these fast. It's not just about multiplying these numbers fast. It's about knowing where to put what. I know I shouldn't put a 10 over here and a 6 over here because 7 times 10 is just too big to be able to subtract or add something to get me to 32. That's kind of the portion of being really good at times tables, just knowing with number sense what it is you should and shouldn't even try. That's what makes this easier or more efficient as you keep practicing it. Anyway, that's your final answer for that. And now I'm done talking about those. So let's just do a lot of factoring the following quadratic trinomial expressions completely. Now, I'll let you know, I have not done these problems yet. Okay? I have not done these problems yet, so I don't know what they factor out to. Some might not be factorable. I grabbed these from a website, I put them in, and then I'm going to go off and do them. Now, the first ones I'm going to factor by grouping, the first 4. The next 4 I'm going to factor using generic rectangles. If you're in to watch these parts of the video, go ahead and watch those. After that, I'm going to do the next slide, and I have 10 problems to do that I'm going to use mental factoring. I'm going to use mental factoring. I have not done a single one of these problems here, that you can guarantee. So when I have trouble and I struggle through a problem, or if I do it fast, you'll know that it was genuine. Now, the mental factoring, like I said, it might take a while, so we'll see how we do there. Okay. So first things first with these problems here, before I ask myself what 2 numbers multiply to these and add to this, I'm going to make sure you can't find a common factor here. Nope. Nothing can divide that 3 out or anything else. So let's go ahead and start factoring. What 2 numbers multiply to negative 15, that's the 3 times negative 5, and add to negative 2. So for 15 here, we're going to test 1 and 15, and 3 and 5. Because the 15 is negative, and because the 2 is negative, then 1 negative, 1 positive, and take the larger of the 2 and make that negative. So it looks like it's going to give me negative 2 here, the 3 and the negative 5. Awesome. I'm going to erase all that now because I'm actually not going to be writing this very much. I'll let you know that right now. This is not something I generally do. I will say it. You'll have to hear it. Maybe write it down for yourself. Try it for yourself. But I'm generally not going to be doing this very often. I want to save space. So 3 times negative 5 is negative 15, and 3 minus 5 is negative 2. So I'm going to rewrite this as 3p squared plus 3p minus 5p. That was my 3 and negative 5, and minus 5. Now you notice I could have written the negative 5p first, but I kind of like to line things up that I already know I can start factoring a number out of here. That's my personal preference. That is my personal preference. You can write it the other way, still find a common factor, and you will not have an issue. You'll still find your answer. But the one that I chose here makes me feel a little more comfortable with what I had here. Now I need to get a p plus 1 inside here. You can write this to begin with. And you're saying, what do I have to factor out to give me that? Obviously not a 5, but a negative 5. That'll give me the p plus 1. That's going to help. Now that p plus 1 is a common factor in both terms, I'm going to factor that out, and I'll be left with 3p minus 5 in the other set. And there's factored form for that one. That's your answer. By the way, how will I know if nothing's factorable? If I couldn't find two numbers that multiply to negative 15 and add to negative 2. Once I got that answer to that question, the rest should be factorable. So you should be good after that. Okay, number 2, no common factor. So I'm going to go ahead. What two numbers multiply to negative 18 and add to 3? So I'm going to try factors. Now, negative 18 is negative, 3 is positive. So I'm going to do 1 negative, 1 positive, the larger number positive. So 18 minus 1, no. 9 minus 2, no. 6 minus 3, yes. 6 and negative 3 are going to be my two numbers here. Now, I could write minus 3n and plus 6n, but I like to divide this 2 out, so I'm going to write plus 6n minus 3n. Again, personal preference. You can do either way, it will still work. I can factor out a 2n, and I'm left with n plus 3. I can factor out a negative 3, and I will have n plus 3. Now, I wouldn't just write it out and say, oh, absolutely, that's going to happen. Make sure of it. Make sure of it. Make sure you did your math right. Make sure you're practicing that math there. N plus 3 is a common factor of both items right here, and I'll be left with 2n minus 3 here. Okay. So these problems aren't that bad. There's more to do, and these steps are weird, but once you know how to do them, they're not that bad. But these problems are still so much easier to do. Once you answer this question, the two numbers there just become the result. What two numbers multiply to negative 35 and add to negative 2? Oh, negative 7, 5? Okay, I'll just write them in. You notice here, though, and I gotta stress this more and more, my two numbers, 6 and negative 3, were not my answers here. Negative 3 was, but notice where I got 6 from. 2 times 3. 2 times 3. But this number was not a 6 right here. That's not how you write the answer. Okay, number 3, 3n squared minus 8n plus 4. No common factor, so I'm going to begin. What two numbers multiply to 12 and add to negative 8? 12 is a positive number, 8's a negative number. Both my factors will be negative because negative times negative is a positive, and I'll have a negative sum. Negative 12, negative 1, no. Negative 6, negative 2, yes. So, negative 6, negative 2. Which one do you think I'm going to write first? That's right, the negative 6. N minus 2n plus 4. Factor by grouping. These both have a common factor of 3n. N minus 2. Now again, I need to get an n minus 2 here. Notice how this is a plus right here. Somehow it obviously needs to turn into a negative, and this one's a negative. I need to turn into a positive. So again, I'm factoring out a negative 2 there. And then I'll have n minus 2 as a result. Factor out the n minus 2, and I'll be left with 3n minus 2 over here. And that factors out. Don't take my word for these. Always double check and distribute. 3n squared minus 6n minus 2n plus 4. Okay, and then those add to negative 8. Okay, that works. 5n squared plus 19n plus 12. Okay, no common factor. What two numbers multiply to 60? Ooh, we tried those. Well, we talked about those a little bit. And add to 19. This time I'll write some out for you just to indulge you a little bit. Both numbers have got to be positive. Positive product, positive sum. 1 and 60, 2 and 30. By the way, I'm going to mentally add these in my head. 1 plus 60 is 30, no. Or 61, no. 2 plus 30 is 32, no. 3 plus 20 is 23, no. But getting close. 4 times 15 is 19. Okay, 4 and 15. There they are. So I'll do 5n squared. Normally you'd see me write plus 15n, right? I'm going to do plus 4n just to really show you that neither way matters. But you can probably see why I would have liked to write 15n, because that way I can divide that 5 out. See, this way I can't. But I can still factor out the n, and I'll be left with 5 plus 4. Excuse me, 5n plus 4. And here I can factor out see, now you have to look a little harder, a 3. And you'll be left with 5n plus 4, as it should be. The 5n plus 4 can be factored out of both, and I'll be left with n plus 3. in the latter half of the problem. Now, notice how, like I said, this is just me. I like to write the larger term for, the quantity with the larger leading coefficient first. I just like to. So I like to write, I don't know if the answers do that or not in general, but that's what I like to do. You can write it n plus 3 times 5n plus 4, and nothing changes. There it is. Okay, there's your factoring by grouping. There it is, there it is, there it is. Awesome. Let's go ahead and use generic rectangles. To be honest, this is my least favorite, only because it takes me the longest. Some other people, it takes them the shortest amount of time because they don't know how to do the others. But if you know how to do the others, they are faster to do. Okay, I hope that makes sense. It's like if you have a really slow automatic car and you have a really fast manual transmission car. If you know how to drive a stick shift, then you'll be able to drive that car faster. If you don't know how to drive a stick shift, obviously you won't be able to take it anywhere, so you'll take the slower car because it's faster for you because you don't know how to drive a stick shift. But if you know how to drive a stick shift, it goes a lot faster. Okay, let's go and get started. 2v squared plus 11v plus 5. Same process in the beginning here. No common factor, but I'm going to find out what two numbers multiply to 10 and add to 11. I'll just tell you right now it's 10 and 1. 10 times 1 is 10. 10 plus 1 is 11. So I'm going to write out in a rectangle 2v squared and 5 opposite each other. And that 10 and 1 that I said, the two numbers that multiply to 11, or that multiply to 10 and add to 11, that 10 and 1, I'll write here with an n as the linear terms. This is my 2v squared plus 10n plus 1n plus 5 that we would do factoring by grouping with. Now what we're going to do is say, okay, well, this v squared must be from a, wait, why are these n's? My bad. I'm not even paying attention to the problem. Somewhere I started saying n. This v squared comes from some sort of v times v. And that makes enough sense because this v times something should give me 10v, and this v times something should give me 1v. But this isn't just v times v, because this is a 2v squared. So where does the 2 go? Well, the 2 is one of these two things. Not sure which one yet. If I try a 2 right here, 2v times something's 1v? I don't think so. It's going to be this one here. 2v times 5 is 10v, and v times 1 is 1v. So your final result, this times this, gives you all of that, and this is the sum of these sides here. That's a 2v plus 1, and over here's a v plus 5. And that's your final result. Okay. Number 6. 2n squared plus 5n plus 2. Again, no common factor. So what two numbers multiply to 4 and add to 5? Kind of looks the same as this one here. It's going to be 4 and 1, right? 4 times 1 is 4. 4 plus 1 is 5. So this is probably where I got my n's. I was probably looking at this. Probably saw this problem really quickly. 2n squared, 2. 4n and 1n. Remember, these should add to become 5. So once again, we're looking at an n times n scenario where one of these should have a 2 on it. Obviously not this one, as we saw last time, so this one should right here. 2n times 2 is 4n. n times 1 is 1n. So I'll end up having 2n plus 1 times n plus 2. Now I feel like if I do these 4 problems, you will really see how these work out. It does pan out to be quite all right. Now, before I move on to the next problems, I just want to reveal that so far all these problems had prime quadratic coefficients. As long as they're prime, this process and the mentally factoring process will be very good for you. If they become composite numbers, sorry, this number's not prime, but I'm seeing something in this problem already that's going to make it prime. If they're composite numbers, you have more things to test. Number 7, 7a squared plus 53a plus 28. Is there a common factor? Almost. These can divide by 7. 53 cannot. 63 could, but 53 cannot. So we're stuck with these. So I have to do 7 times 28, which I don't know what that is. 196. Great. Now I have to choose numbers that multiply here. So this is where I might start writing out some numbers. Now, 196 is positive. They have to add to 53, which is positive. I have to find positive set. I should not test 1 and 196. You know that's not going to add to 53. I have to test two numbers that are less than 53. Meaning I have to test two factor pairs that multiply to 196 that are less than 53. Well, I know 14 times 14 is multiplies 196, but of course that equals 28, which is not the number we're looking for there. We're looking for a 53 here. Clearly, I need to do an even number times an odd number. That's neither here nor there. Let's figure out other numbers here. I believe 180, 16 and 10, 11, no. I'm sorry, not 16. I meant 6. 6 times 30 is 180, so 31, 32, 33. 6 and 33 multiplied 196. Oh, no, they don't. I'm sorry, that's 198. So you know what? I just got to start testing numbers here. That's the gist. That's the overall gist here. 18, no. 19. See, I legitimately don't know this answer. I got to try numbers just like you would. 20, 21, 22, 23, 24. 24, 96, no. 25, 26. You know, I'm sorry when I run into this kind of stuff. This is the struggle. By the way, these might not be factorable. That's the other thing. Okay, you know what? Let's go ahead and write out the list. Let's write out the list. 1 and 196, no. 2 and 98, no. 3, this cannot divide by 3. 4, it should be able to divide by 4, right? 50, 49. 40, here it is, 4 and 49. 4 and 49, there we go. And that was as legitimate as I said. See, maybe I should have tried the smaller numbers first just because somewhere eventually these numbers will start reducing. So 4 and 49 work, and those are the numbers that go here. So let's go ahead and write this one out. 7a squared, 28, 4a, and 49a. Now, as 7 is a prime number, it's good because when I do my a times a, it's only just going to be a 7 in one of these two places. Clearly, it's not here because we're not going to do 7 times 4. It's going to be here. By the way, 7a times 7 is 49, and a times 4 is 4a. So my final result will be 7a plus 4 times a plus 7. I wish I had my easy button. Say, that was easy. Not that it really, that's the sarcastic part of it. You get math jokes. And our final problem I'm going to use generic rectangles on is number 8. Factor 9k squared plus 66k plus 21. Okay, I'm going to save you a lot of struggle right here. There is a common factor. Not of 9, unfortunately, but it's of 3. I can factor out of 3, and I'll be left with 3k squared plus 22k plus 7. First of all, you know how we're doing these problems here, right? We're taking what two numbers multiply to 3 times 7, that 21, and add to 22. By the way, that's going to be 21 and 1. I already found my numbers. The other way you would have had to do this is ask what two numbers multiply to whatever 9 times 21 is, 189, and add to 66. See how much trouble I had with this last problem? Don't you think that would have taken me just as long over here to find the two numbers that multiply that and add to that? Yeah, it really would have. That would have taken me a long time. So you will thank me when I tell you to find common factors first. Even though this didn't become a 1, I have significantly reduced my value, so much so that I saw this answer right off the bat. 21 and 1 are those two numbers that multiply to 21, 3 times 7, and add to 22. So let's generic rectangle it up. This is going to be my last generic rectangle problem. After that, it's only mental factoring. I have a 3k squared here. I have a 7 here. And I have a 21k plus 1k right here. K times k, 3 is a prime number. That's good. So a 3 would go here because 3 times 7 is 21. 3k times 7 is 21k, and k times 1 is 1k. There we go. 3k plus 1 times k plus 7. The only reason why I said that this one is slower than this one is because, number one, I'm spending time drawing a stupid rectangle. Number two, if this is a composite number, it does take longer. So in a best case scenario, no, it might be faster than factoring by grouping. In an average or worst case scenario, it might be slower. It depends on the problem. Okay, I'm done with those. Finally, I'm going to look at factoring quadratic trinomials mentally. Ready? Okay, number 9, 15n squared minus 27n minus 6. You know what's going to save me? A common factor of 3. That's right, kids. We have 3 times 5n squared. Oh, you know what? Hang on a second. I messed up on a problem. This, what did I leave out? This 3 goes here. I left it out. Here it is. There it is. That's my answer. I just made it the biggest mistake here. That's a 3 times all of that. My bad. That's something I don't like about this. There you go. Here we go. 3 5n squared minus 9n minus 2. So when I write my final answer, see, this is one thing I also like about this. I won't forget this 3. I'm going to write it immediately. If I have something factorable, it's going to look like this. If I have something factorable, it's going to have an n times an n somewhere. But better yet, how do I multiply these to get 5n squared? Well, it has to be 5n times n. So I'm going to go ahead and just write the 5 right here, because 5 is a prime number. That makes it easy. These are already locked in place. We have a negative product and a negative sum. That means that, well, that means one number is positive, one number is negative. And I don't know which one's negative necessarily. It could be the larger, it could be the smaller. Why could it be the smaller if this is a negative sum? Well, because if I choose a smaller number and I multiply it by 5, that might be larger than a larger number than this multiplied by 1. So what are the only numbers I'm going to try? I'm going to pick factors of negative 2. So either negative 2 times 1 or negative 1 times 2. And I got to figure out where they go. So there's only one of 4 options I'm going to try here. Now, I actually do these mentally. I'm going to write this one out for you. But most of the other ones I'm going to do mentally. I found the answer a long time ago while I was talking already. So I can, and I'm going to kind of intentionally, well, I don't know. There's negative 1 and a positive 2, or a positive 1 and a negative 2, or a negative 2 and a positive 1, or a positive 2 and a negative 1. So let's try 5n minus 1 times n plus 2. That would be 10n minus 1n. That's 9n. That's a positive 9n. So that's the wrong answer, but it is reverse of the correct answer, as I talked about before. If that's a positive 9n, then this one here will give me negative 9n. So let's switch these out. This one was wrong, but this one here, let's try a positive 1 and a negative 2. 5n times negative 2 is negative 10n. This will be plus 1n, which is negative 9n. That is your answer. I'm done. I've solved it. Don't have to do anything else. Now, again, you don't have to write this out. You could. But if you know what you're mentally doing, storing them, and you're good at your times tables, I knew that this was really close to 10, so I knew I had to multiply it by 5. You know, it's those kinds of things. It'll help you a lot along the way. 5x squared minus 18x plus 9. No common factor. So I'm going to go ahead and start this out. If it's factorable, it's going to look like this. I have an x times x going on. 5 is a prime number. That means I can write a 5 here. Hopefully you're making sense of this. Positive product, negative sum. That also means both of these are negative. Boom. I'm already on the way. Now, 9's a composite number. That means it multiplies by more than just itself in 1. But not too many things. We're going to try 9 and 1, 1 and 9, and 3 and 3. Okay? Let's try 9 and 1. 5 times negative 9 is negative 1 is negative 5. Minus 9 is negative 14. That one's out. Let's try the next one. Hopefully you'll recognize this one doesn't work. 5 times negative 9 is negative 45. No, that's not going to work. If it's factorable, the only way this is going to work is if these are both negative 3, negative 3. You can't guarantee these always work. Sometimes they're not factorable. Negative 15 minus 3. Hey, that's negative 18. Okay, there's my answer. That one worked. Okay, now for the most part, I'm not going to be writing these numbers out. I'll just be saying them out loud. I just want to get you the gist of what's going to happen. I'm not going to write them in here either. I'm just going to say them out loud. I want to show you how fast these can become if you know what you're doing testing them. Well, I might be changing something here now. Number 11, 4n squared minus 15n minus 25. This is an n times n deal right here. There's no common factor, so I know I'm n times n. Here's the difference with this kind of problem, and this is what's going to take this one just a hair longer. I'm going to write out 2 sets just to show you. 4 can come from either 2 times 2 or 4 times 1. So you have more than one thing to check to do these things. Now I'm trying to get a negative 15n, and mentally I'm already kind of arriving at what I think could be a possible answer here. Negative 25 only either comes from 25 and 1 or 5 and 5. So I'm going to mentally be placing in numbers here and see what works. By the way, 1 has to be negative, 1 has to be positive. 2n times, so 2 times negative 1 is negative 2, minus 50, 2 times negative 5, no, that's not going to, or sorry, plus 50 is 50, no, that's not going to work. 5 and 5. Let's try negative 5 and positive 5. Clearly that won't work because this isn't a difference of two squares problem. If this was like that, then it would work. So it doesn't look like the two n's are what I'm going to use here. I'm going to try the 4n and the 1n. Let's see if we can get the answer that way. Let's try 4 with 25. Clearly that won't work. 100. 4 with 1 might work. A negative 1 and 1 with, or a positive 1 and a negative 25. So that'll be 4 minus 25. No, that doesn't work. So my last chance is if I can use a 5 and a negative 5. And if I want my negative to be larger, in this case here, then I want to multiply it by the 4. So I want the negative 5 here, and I'll have the positive 5 here. 4 times negative 5 is negative 20. 1 times 5 is 5. Negative 20 plus 5 is negative 15. Okay, so the last thing I tried worked out there. And again, I'm trying to get, I say I'm not going to write these visuals, but I need some visuals along the way to really get you to feel it out. Really get you to feel it out here. Because the two n's didn't work here. That's when it comes hard, when you can't lock in a prime here. Number 12, I feel like we have the same kind of issue here. No common factor, so I am dealing with a 4. That means if it's factorable, I'm going to do some sort of x times x here. The good news about this one is that there aren't a lot of factors of 49, and that because I have a positive product and a negative sum, I am dealing with a minus and a minus. So either, which by the way, I don't actually write out these two. I do this mentally until I figure it out. But either this is a 4 times 1 scenario or a 2 times 2 scenario. So my factors of 49 I can try are either 49 and 1 or 7 and 7. Let me try the 7s first, because clearly the 49s won't work here. If I multiply 2 by 49, I'm already way past 35, negative 35. So this is negative 14 minus 14. That's negative 28. It looks like this won't give me the result I want. So I'm going to look to the 4 and the 1. And the only way this would work with a 49 is if the 49 is here, because I want to multiply my 49 by 1. I sure as heck don't want to multiply it by 4. But you might have also noticed here that 1 times 49 is already larger than 35. So that won't work either as long as both of these are negative. So the only way this is possible is if these can both be 7s. If they can't be, then it's not factorable. 4 times negative 7 is negative 28. Minus 7 is negative 35. Okay, it worked out. That's your final answer. Okay, this time I'm going to try and speed up for you. I'm going to, I want to show that these can be fast if factorable. No common factor. So I'm dealing with an n times n case. It's either 2n or 2n times 2n or 4n times 1. I'm going to try 2n times 2n visually in my head. Positive product, negative sum. Both numbers are negative. Factors of 4 are either 2 and 2 or 4 and 1. So I'll try 2n with 2n, and I'll try 2 and 2. That'll be negative 4 minus 4, negative 8. No good. Negative 4 minus 1. 2 times negative 4 is negative 8. Minus 1. 2n minus 1 is negative 2. That's negative 10. That won't work. So the 2's are out over here. I'm going to try 4 and 1. 4. So 4 and 1 would have to be it, otherwise it won't work. 4n times negative 4 is negative 16. 1 times negative 1 is negative 1. Negative 16 minus 1 is negative 17. There it is. 4n minus 1 times 1n minus 4. That one's pretty cool. 6x squared plus 7x minus 49. How unfortunate. Once again, no common factors. So 6 is also a composite number. You can either do 6 times 1 or 2 times 3. Good news about this is, actually this is bad news. Negative product, positive sum, I don't know which is which and where. Let's try the 6x with 1x. Those tend to work out a little more recently. 49, multiples of 49 are 7 and 7. Obviously, I'm not going to multiply the 6 by a negative 7 anywhere to get a positive 7 out, so I don't think the 6 is going to work here. Only way this is possible is with 2 times 3. So again, that's me doing times tables fast. Let's try 3 and 2. Let's try the 7 and 7 scenario here. First, I'm going to try, because it's a positive result, I want the 2 to multiply with the negative number. And I'll try the positive number here. So that's 21 minus 14. That gives me 7. Boom, I got my answer. And again, I haven't done this problem before. That's I tested other numbers. It didn't work. I got my answer. 6x squared plus 37x plus 6. I really want something to be have a common factor. Hang on, let me look down the list. Okay, this has a common factor. That's good. The other ones look like they don't. 6x squared plus 37x plus 6. X and x. They'll either multiply 6 and 1 or 3 and 2. Let's try the 6 and 1s. Oh, yep, 37. How am I going to get that? I better multiply the 6 by a 6. 6 plus 1. Boom, there's my answer. See, it is the first thing that I tried, but I mentally started to tell myself, how am I going to get a 37? How are these going to both be positive? You know, so it's the first thing I tried, but I tried it based off selectively filtering in my head what I should have multiplied. You could have tried a bunch of other numbers here, the 3 times 2 and 2s and 3s and all here, but these should have definitely been pluses, but I found it. Right? Again, this is 6x squared plus 36x plus 1x plus 6. I know my factors of 6 really fast. I say I'm going to be multiplying a number by 6 for this to work. 6 times 6 I know is 36, and it's really close. You know, that's how I'm getting these answers here. That's how I am. Okay, number 16. Now, there's no common factor. But what? Factor out this negative. You'll thank me later. Factor out this negative. Plus 25a plus 25. By the way, if this answer is not factorable, I won't write not factorable for this because I did factor out something. I factored out a negative 1. It's not our favorite factor. I'd rather factor out a number. But that doesn't mean it's not factorable. I did factor out a negative 1, so it is factorable. And by saying I factored out a negative 1, I mean I made it better by factoring out a negative 1. You could factor a negative 1 out of this too. That doesn't mean it's factorable that way. I don't want negatives all over the place here. All right, so I'm going to leave the negative on the outside. If this thing here is factorable, I'm going to be looking at some nice old set of values here, a and an a. These are all positive, so I'm looking at a plus and a plus here. We're either looking at a 3 and 2 scenario or a 6 and 1. I'll try my 6 and 1 again. 25, either 5 and 5 or 25 and 1. Only way that the 25 would work is if 6 multiplied with the 1, but 25 plus 6 is 31. So it's not 25 and 5. Only way possible is if this is 5 and 5. That's 30 plus 5, which is 35. So it looks like the 6 and 1 are out. That can't be those ones. Let's try 3 and 2. 3 times 5 is 15. 2 times 5 is 10. 15 plus 10 is 25. All right, that works. That's my final answer. If you still don't understand the mental factoring at this point, I don't know if I would practice it. This is for those who understand what's going on here. Last two problems. 6n squared plus 5n minus 6. Again, composite value. It's unfortunate, but I'm dealing with it. I have an n times n here. I guess these problems are kind of challenging. So either 6n and 1, negative product, positive sum. So one's negative, one's positive. Pick my factors of 6, make it multiply, or make them add. You know, make this add to a 5 while foiling out. So let's try some numbers here. I know I'm not going to multiply 6 by a 6. That'll just give me something too large. Let's try multiplying it by the 1, though. Let's try a 1 and a negative 6 here. So that'll be 0. So no, that shouldn't work. You know what? That shouldn't work anyway because these are common factors, and I would have been able to pull those out if so. So the only way that 6 and 1 would be possible is if I have a 2 and 3 here. Let's try the 2 and 3. 12 minus 3 is 9, so no. And obviously 3 and 2 wouldn't work. So it looks like these ones are out here. So let's try 3 and 2. And let's try those with 6 and 1. I don't want 3 to multiply with that 6. So I might try it with the 1. 3 and a 1 and a negative 6. Try something like that. 3 minus 12. No, we're still getting kind of the same issue as we had before. Let's try 3 and 2 with these. 3, I think this will be it. Plus 3 minus 2. That's 9 minus 4. Okay, that's 5. So that's your answer there. So, see, it took me a while writing those ones out, but got it. All right, number 18. Hopefully you divide something out here. These all divide by, it looks like the most they divide by is 4. I was going to say 8, but these don't divide by 8. So 4b squared plus 15b minus 25. Did we have 4b squared? Hey, look at this. 4n squared minus 15n minus 25. I'll show you how we can then get the answer here. You don't call it cheating if you're going off your own work. But anyway, what if you had to choose these numbers? What if you multiply numbers that came to 16? 1 and 1, 4 and 4, 2 and 8, and 100 has 1 and 100, 2 and 50, 4 and 25, 10 and 10. Way too many things to try. Factoring out is good. If I can factor this, which I can, my result will look something like this. Guess what? This is 4b squared plus 15b minus 25. This is 4n squared minus 15n minus 25. So you see how the positive 5 went with the 1 and the negative 5 went with the 4. By that I mean through multiplication. I'm just going to switch that. I should have 4b minus 5 times 1b plus 5. See, the fact that I mentally saw these numbers in my head and say, hey, we did those before. By the way, that's not a 16. That's a 1b. Let me just write b. It's a b and a b. Let's double check that one. 4b times b is 4b squared. 4b times 5 is 20. 5 minus 5b minus 25. So that's 4b squared plus 15b minus 25. So, okay, that one worked out. So it looks like this is your answer here. And remember, there was the 4 out in front. It stays out in front there. I am done. So just to recap, we looked at factoring as a whole. We looked at common factors and factoring out leading negatives as well. We looked at factoring by grouping, factoring with generic rectangles, and mentally factoring. I'm done. Fing!